Okay, let's talk about r to the k, or the vectors over r. So this is a vector space, and the main use of r to the k in calculus is as a vector space, as an inner product space, actually. And these uh, inner product spaces um, are known as Hilbert spaces, after David Hilbert, who was a real famous mathematician around the turn of the 1900s, the 20th century. Um, he studied these a lot and sort of saw how useful an inner product space was, and you can kind of do calculus and things like that on these inner product spaces, and you don't necessarily have to have the reals or the complexes to do inner product space stuff on. You can do them on sets of functions, you can do them on all kinds of things, and it's really these sort of basics that allow the calculus type ideas to work in these more general spaces. So we're going to talk about vector spaces with an inner product. And so to do that, we're going to have to define vector spaces, we're going to have to define inner product, and we're going to have to see how that works to give us a topology so that we can find limits and we can measure distances between things and sort of do all of those calculus things that we've done a lot of here this semester. So let's start with a vector space. So a vector space over a field F, and typically that'll be the complexes or the reals. You can do these over finite fields as well. If you've got some algebra background, you might know what a finite field is, but typically our field is going to be the complex numbers or the real numbers. We'll define everything with the reals. There's a couple differences that I'll talk about. I'm not going to write down for the complexes because you have to have complex conjugate things show up when you're dealing with inner products. But we're going to define everything over the reals so we don't have to worry about complex conjugation or anything. But everything does work on the complex numbers as well. So a vector space over a field F is a set V with an operation plus, so that the following hold. Okay, so I want, if x, y, and z are vectors, that x plus y plus z makes sense whether I put the parentheses there or whether we put the parentheses there. So I've got addition is associative. I also want it to be commutative. I want there to be a zero element, a zero vector in V. And I want x plus 0 equal to 0 plus x, which is equal to x. Sometimes I draw the bar over it, so it's not just the number 0, it's the vector 0. I should maybe draw bars over all of these things, but in context, we're going to be talking about vectors most of the time, so I might not draw those bars all the time. Okay, and then I also want additive inverses to exist. So for all x in V, there exists a minus x in V with x plus minus x equal to minus x plus x equal to 0. Okay, so I've got addition of vectors, but there's this field associated to it, and I haven't really talked about that field at all yet. So there is also scalar multiplication exists for any scalar c in my field. We have a function c times v is in the vector space again. So I can scale up or stretch out vectors in some sense. So for all v in v, c times v is in v. We want c times d times the vector v to be equal to c times d times the vector v. So scalar multiplication is associative. Okay. I do want, if I take 0 times a vector, I want to get the 0 vector. And if I take any number times the 0 vector, I should get the 0 vector again. And the last thing I want is, I've already got associativity in the field, so I don't have to write down associativity of scalar multiplication. But I want the distributive property. I want to link scalar multiplication and vector addition together. So I need the distributive property. And we need that in two different ways. I need that if I add scalars together and then multiply them by a vector, we could take the scalars times the vector and the other scalar times the vector and add them. Or if I take a scalar times the sum of two vectors, I get that scalar times the first vector plus that same scalar times the second vector. So I've got the distributive property, I've got the nice properties that we know and that we understand from just our experience using vectors in the reals. But you can do this with other things as well. For example, if I take two polynomials and I add them together, I can add them in any way. Three polynomials together would give me, I can associate the addition of polynomials. I can do commutativity with the addition of polynomials. There's a 0 polynomial, which is just the function that gives you 0 everywhere. You can scale up polynomials by multiplying each of their coefficients by a number. And the distributive property works on polynomial multiplication and addition, right? So the set of polynomials are a vector space. They're not typically the vector space that we use when we're thinking RK, but they're a infinite dimensional vector space. RK is a k-dimensional vector space. There's this idea of dimensionality that we can apply to vector spaces as well. I don't think we're going to have time to get into that in this video, but there's many books that discuss that. Linear Algebra Done Right is a very good linear algebra book, and it talks about how you can abstract things a little bit, and you don't necessarily just have to think about linear algebra when you're dealing with Rn or Rk. Some examples of these then, let's just write down. So Rk is an example of a vector space. This is k-dimensional. We had the set of polynomials. We'll get a little scripty p, and it'll be the set of the sum from I equals 0 to n of ai x to the I, where n is in the naturals including 0, and ai is in the reals. So that set of all polynomials with real coefficients is countable dimensional. It's infinite dimensional but countable. And if I take the continuous functions on the reals, where this is the set of f mapping the reals to the reals, such that f is continuous. We've learned in this class that if I add two continuous functions together, I get another continuous function. I can treat the always zero function as the zero function or the zero vector. I can multiply continuous functions by a number and just stretch them out or shrink them down and scale them and get another continuous function. So these are infinite dimensional and these are uncountably infinite dimensional. Oops, that's not what I wanted to do. Okay. So those are three examples of vector spaces that we have. Each one of these actually can have an inner product put on it. And the inner product is what allows us to do the topology stuff. We can take the inner product and we can get a topology on these sets, these vector spaces. So let's state what needs to be done for an inner product. So an inner product is a function associating the vector space to the field, to its field. And we're going to write this with angle brackets, and I'll put in some dots to represent that the inputs, there's a first input and a second input where those dots go. So this is a function that takes a vector space cos itself. So it takes a vector and puts it in the first spot, it takes a vector, it puts it in the second spot, and it outputs an element of the field. Okay, there's a few things that need to happen for an inner product to actually be an inner product. So the inner product when the field is the reals, let's just write this down for the reals. So we're going to get a real number we'll put the reals, because these do generalize, but things are a little bit different when you're dealing with the complexes, because you have to use conjugates and stuff like that with this. But with the reals, I don't have to worry about conjugates. I can just make this definition a little bit simpler. So I want x inner product with y to equal y inner product with x. So I want symmetry. I want that ax plus by with z. I want linearity. So I want a x with z plus b y with z. And remember, these are all real. I'll put vectors on the x, y's, and z's because those are the vectors that are being input. But the a and the b are scalars. So these are A and B are scalars. So this is a number times the result of the inner product is a number, and the result of the inner product is a number. So this gives me another number, as it should, because this is a number. So the inner products, remember, always give you a number or a scalar from the field back out. So this is linearity. I've only written down linearity in the first input, but by symmetry, you get linearity in the second input as well. And then the last thing I want is positive definite. So if I take an inner product with itself, you're going to get something bigger than or equal to 0. And with equality, only when x is equal to the 0 vector. Okay. And this is called positive definite. Okay. So with these three things, we have an inner product. The reals have a standard inner product that you've probably used before. It's called the dot product. RK typically uses the dot product as the inner product. And the dot product says if I take the vectors x and y and I dot them together, what do? I add up xi times yi from I equals 1 to n, and that result is my dot product. This is sometimes written as x dotted with y, right? But the angle brackets are also very common notation. Calc books sometimes use either one. I think a lot of times they use the dot product because they like to call it the dot product, as opposed to like the cross product of two vectors, which is an entirely different thing because a cross product takes two vectors and gives you another vector. And that works really well in R3. It gets pretty convoluted if you try and do that in higher dimensions. You can still do it, but it only really works well in R3. So why does this allow us to do topology on this vector space? Let's maybe see one more inner product. Let's look at an inner product between some integrable functions. Say I have two functions that I can integrate, and I want to take the dot product between f and g. Well, a lot of times, just like we did with the dot product, what we can do is we can take f of x times g of x, and we can integrate that product over whatever the domain is, right? And that will give us a nice inner product as well. You can see that if you dot a function with itself, you get f squared, which is always going to be non-zero, and so you'll have the positive definiteness. The linearity of integration gives you your linearity of the dot product or the inner product, sorry, and your symmetry comes from the commutativity of the outputs of those numbers. So you can do inner products with integrable functions in this way. And there's other ways to do inner products. There's a lot of different ones out there. They typically are used to find differences in bases or how you write down things in the vector space. In RK, we typically have components, and the first component means how far you travel in like the x direction. The second component, how far you travel in the y direction. The third component, how far you travel in the z direction if you're dealing with R3. Well, there's different ways to write down how to get to points in space, And maybe you don't want just a orthogonal set of axes. You want to grid things up differently. Well, you can use a different basis to write down where things are in space. And different inner products allow you to do different things with that type of stuff. Okay, but how do we get to a metric from an inner product? Well, the first step is we're going to define a norm. And sometimes you'll see these things, you've probably seen them before. A norm of a vector is a function with double bars, and it's going to take the vector space and it's going to send it to the field again, which we're going to say is R. And it's going to satisfy a couple things. It's going to satisfy that the norm of x is bigger than or equal to 0 with the norm of x equal to 0 if and only if x equals 0. So we've got that positive definite idea again. And what else do we want? We want that the triangle inequality holds. So if I take the norm of two things and I split it up, it's smaller than the norm of the sums of the individuals. So those two things give me a norm, and we can get these from the inner product space pretty easily because those are very closely tied to this and some of the other geometry we get allows us to do the triangle inequality. Okay, so what I want to say is any inner product produces a norm by defining the norm of x equal to, well, it's going to be the square root of the inner product of x with itself. I want to use the square root because that's going to allow us to get that triangle inequality a little bit easier with things, and it's gonna work out a little bit nicer for our measurements. And this norm is going to give us the Euclidean distance in RK, which is what we're typically used to, where you take the difference between each of the components, square them, add them together, and then take a square root. Okay, so this norm that we get from here gives us a metric on RK. Gives us the Euclidean, specifically Euclidean metric. How? Well, the distance between two vectors is just going to be the norm of their difference. And that would be, well, it would be the inner product of x minus y and x minus y to the 1/2. Okay, so this is the square root of x1 minus y1 squared plus x2 minus y2 squared plus dot 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 plus xk minus yk squared, right? And that's the typical distance measurement that we see when we're dealing with things in RK. All right, so all of these things allow us to do and put a topology our standard topology where we have this is our distance between objects, so we can take limits using those epsilon neighborhoods and ideas that we had when we were talking about metric spaces on these vector spaces. And it's really a powerful tool and generalizes really, really nicely, because now we can kind of do some of this calculus stuff in RK. We can do it on the set of polynomials. We can do it on the set of continuous functions. We can do it on some really abstract sets that we have proven are vector spaces, and you can get nice results about what things are integrable, what things are differentiable, what's it mean to be a derivative in RK, and that type of thing. I hope that is not so vague that it's not useful, but it's not so specific that it's too esoteric or not applicable either. So I think I'll stop there, and I'll talk to you later.